Okay, we're going live. Hello, everybody. I've seen a lot of people in the chat room already. Thanks for joining us. If you can hear me, please give me a yes. Please post a message. Just make sure that the sound is okay. Okay, great. Okay, everybody can hear us. So welcome to another Launch and Learn series of ACE. My name is Xiyang. I'll be your host to relay everybody's questions to our speaker today. Our speaker today is Rohollah Soltani. Rohollah Soltani has been a machine learning scientist for more than 8 years, with a blended industrial and academic experience in machine learning, deep learning, representation learning, and natural language processing. He has been working on anomaly detection for the past 2 years in health insurance related fields. So without further ado, I'll pass the mic to Rohollah and let him to tell us a little bit about the overview field of and the state of anomaly detection in 2019.
Thanks, Shane, for the introduction. So this Launch and Learn is going to be like an overview of some of the concepts and methods that we will actually discuss them in more detail in our upcoming workshop. So here we're going to say that what's anomaly detection, what's novelty detection, and how we can handle them, and what's the methods and application and all the thing about them. So detecting outlier or anomaly is one of the core problem in machine learning, and it has recently become an active research topic with the exploding growth of big data and AI technique in lots of applications. And that's one of the reasons that we are doing this workshop, so we can learn what's going on in this field and how we can actually tackle all these problems. So first, I guess we should start with the definition. What is anomaly? What is the definition of it? If you just look it up in the Oxford Dictionary, it would say that it's something that deviates from what is standard or normal or expected. But people will refer to it with different names like outlier, novelty, out of distribution, rare event detection, or all those things. But all of them are kind of referring to the same concept, which means if something is not following your normal behavior or your normal system, you can call it like outlier or novelty or anomaly. And this session is how can we actually catch them, or how can we actually see how can we treat them, how can we detect them, and how can we actually find them and maybe clean our data or all those things. So anomalies are pattern in the data that, as we said, is not similar to the rest of the data that we have, which is a normal data. Its nature can be in a two way. It can be as they call point anomalies, which is like a single instance of a data, which they are like too far from the rest of the data. Like a business case for that can be detecting a credit card fraud based on an amount, a big amount. Like if suddenly you have, let's say, I don't know, $5,000 in your credit card, and they can say maybe this is a fraud because that price, that number is super different from all the rest of the number that you have in your credit report. The other type of anomaly can be those contextual one, those who are kind of dependent on the context as well. So the abnormality is context specific. This type of anomaly is common in maybe time series data. So another business case for that can be, if you're going to refer back to the credit card, it can be spending maybe $100 a day if you are in vacation is okay, but other than that, maybe it's not normal. Or something like temperature, having a warm day in January in Toronto is outlier, but maybe in the rest of the year, maybe in the summer, maybe it's not that much outlier. Or maybe in a stock market, if you see some like spike in the stock market, and based on the context, you can say, well, something is happening. It can be maybe a tweet from a president that changed in the market or something like that. But you can say that the price itself is not outlier, but given the context, which was all the number that you have seen maybe in the previous days, this can be called anomaly here in that context. So what is the application of it? One of them, it can be in like an intrusion detection or fraud detection. Fraud can be in banking or in insurance, in finance, or for insurance can be for car insurance or health insurance. In fraud detection, if a card is stolen, the purchasing behavior of the card usually change. Maybe the one who's stealing the card will buy stuff that you are not buying regularly. And that's how you can detect some abnormal or outlier pattern in the data. Same thing can goes with the unauthorized access in computer network, which result in like some unusual pattern. Detecting this abnormal pattern is essential for your network security. Some of the other applications can be in industrial damage detection or in medical and public health. In healthcare, you can say that healthcare is an integral component of people's lives, and actually waste, abuse, fraud are actually these are the things that drive up all the costs in healthcare by tens of billions of dollars each year. Healthcare insurance claims fraud is a significant contributor to increase healthcare costs actually, but its impact can be reduced by detecting those fraud. And actually, one of the things that we are doing in Notion is we are working with different healthcare companies and insurance companies to actually find those kind of fraud for them using different machine learning and deep learning techniques, which is one of the essential part of the insurance companies. And the other thing in healthcare is finding some rare event. Is like, I guess lots of people nowadays wearing a smart watch. So those watch recording ECG signal. So given all those signal, or even in the hospital, having all the signal from your heart, from different parts of your body, sometimes you can detect some abnormal behavior, like maybe heart failure or stroke. You can detect them, and then you can notify the user or the doctor that something rare is happening, and that patient needs attention. So for other applications, can be for image processing, in a text, in sensor network, and nowadays we are saying that in recent times you're seeing fake news in all over the places, or in social media. It has given a platform, have given a platform to people to be able to use and spread news and maybe fake news. And sometimes it's actually difficult to differentiate between real and fake news. And one of the application of anomaly detection is be able to tell the difference here. What is not normal, what is different based on the context and based on all the behavior that you can see from that context. Or the other thing that you can just use is you can just simply use it to clean your data and improve your model performance by removing noise or some outlier from the data, so you're making it easier for your model to be able to predict or to do classification or whatever you want to try to do with your model. Since picture usually say a lot more than words, you can see that in different application you can use anomaly detection given a logs of network, signals, and image. Or like having a camera in different part of the city, you can actually detect illegal traffic flow. Or you can detect anomaly. The detecting anomaly can help actually in predicting accident in traffic pattern for autonomous driving car. Like if you are sensing, if you're looking at the road and different place in the street, if you see some unusual behavior, it can actually help you to see that maybe some accident is happening or something unusual is happening. You have to alert the driver or something, or ask him to do something about it. So okay, system 1 and system 2. For those who attend NeurIPS this year, Benju made have a presentation about from system 1 deep learning to system 2 deep learning, which was super interesting, which was based on the book Thinking Fast and Slow, which I read a while back. No, when I was thinking about it, it was a cool concept even for anomaly detection, because the idea is like a human are always watching for something weird or out of ordinary, and our brain is in constant state of finding anomaly. So in his book, he's saying that we have like a two system of thinking, system 1 and system 2. System 1 and system 2 are two distinct mode of actual decision making system. System 1 is like automatic, fast, and often unconscious way of thinking. It's autonomous, it's efficient, it's require little energy, but it can be biased, or it can make actually systematic error. It's like when sometimes you're even driving home, you're there and you have no idea how to get there because system 1 was doing all the things for you. It's fast, sometimes most of the time reliable, and that's why you don't have to think or reason or do something about it unless you see something unusual. And that's when system 2 actually kick in. So system 2 is like a slower, more analytical method of thinking that will take over if system 1 asks for it. So which we are using it for, I don't know, more analytical thinking, planning, and reasoning. And it's our instinct, or as the book says, system 1, that provide anomaly detection, so we can actually identify things that violate the internal model of the world in your brain. So this is the system 2, which is the slower part, is more on an analytic way of thinking that will take over once we see anything unusual in the world. The funny thing that the book is also saying that system 2 is always lazy, and the brain doesn't want to work that hard. So most of the time is relying on system 1 unless it's needed. And in machine learning sense, you can say anomaly detection is learning for defining what is normal and using that model for one model of normality to find interesting deviation or anomaly. So, and as Benji was saying in the NeurIPS was like most of the method in machine learning is usually system 1. Is like our supervised model. It's like given an input, we are saying what's the output, what's the prediction. Is like a system 1 that given all the data, which we are assuming that all of them are normal and training data, you want to make a decision fast and just based on the input. And he was saying that maybe is the time that we have to move towards system 2 and make a connection between them and having both of them in place. And as you can see here, to be able to do reasoning and having a better AI or machine learning, you need to have a system 1, which is all those machine learning techniques that we have right now. But you need a trigger that says that, okay, no, that's the time that you need more thinking, more reasoning, more attention in different places of the data because I have seen something unusual. So for me, that was like a cool reason that I was saying myself that maybe that's why we have to think about anomaly detection more carefully, and you have to be able to come up with a better way that they're handling our data. If you want to categorize the different method of anomaly detection, we can classify them in maybe 3 different groups. The first one is supervised, second one is semi-supervised, and the last one is unsupervised. In supervised one it's when you have labeled data in training, and in a test you have labeled data. In training you have positive and negative one, and given a test you have to actually label them, which is like a simple classification algorithm that you can use. It can be neural network, can be any kind of classification methods, because you have a label data here. But one of the problem here is usually the data is super imbalanced, and you can just use those techniques that can handle those imbalanced data. You usually have lots of normal data in your data set and a super few small positive data, like a outlier data in your data set. And the other problem with them is usually you can cover all those anomaly or novelty in your training data because you haven't seen them all, and all those things that you have seen is maybe a few and a subset of all the anomalies that you can see. And usually you will make the model to be super biased toward them, and you will miss lots of other anomaly that can happen in your in real life or in your data. In semi-supervised technique, you have a training data.
If I could interject a little in here, we do have a question which I think is quite kind of related to what you just mentioned. Can you take that question for now, or you want to do it later?
Sure, why not? Yeah.
Okay, so the question is from Neil. The question is there a criteria that we need to follow to differentiate between an outlier and a rarely available class or class with considerably low samples? So basically, he's asking about the criteria on how to differentiate the two.
They can be a similar thing or not. The problem with if you have a class with super small sample, the thing is, you know what is the label of the class, and you know what you know something about the class itself. It means if, let's say, in maybe MNIST, if you remove number 7 from it, and all the data that you have is all the number without number 7, then number 7 is a class that you haven't seen before, and you can say that this is anomaly for me from that moment. But the thing is, you know some property of the class, and you know all the things will be part of that class. The problem in anomaly, or that's what they call it, novelty, is they are something that you haven't seen before at all. You have no idea about them. They are just different. They can be meaningful. They can be just a new pattern or a new ways or a new way of the thing that the system starts generating data. It can be just based on because this year something new is happening, or maybe because I don't know, if it's a stock market, maybe because something has changed in the world, or someone says something about something that you haven't seen or catch before. There's no label for it. It's just different from the rest of the data. And maybe after a while that you have enough of it, then you can say that, okay, that's not different anymore, is kind of like a new normal. But not all of them have the same class. They can be just a noise. They can be from different point in your distribution in the database, in the data set.
Okay, thanks.
Okay, so I guess I was doing semi-supervised one. In semi-supervised one, you don't have any negative you don't have any anomaly in your data. So you're sure about your training data. You're saying that all the data that I do have right now, they are all clean. They are normal. So what can I do with that? So it means then the thing that you want to do, maybe there are some techniques like one class classification. It means then you want to learn the distribution of the data that you have. And from that moment, you're saying that whatever deviate from that distribution is anomaly. It's outlier because it's not following the same distribution. The likelihood of the new sample is super low. And there are different techniques for it, like one class classification, as I said. It means you're making a boundary, or if it's a one class STM, is like a hyperlink over your data. And then from that moment, if something is the other side of the boundaries, you're saying that this is anomaly. In density-based, they want to learn the distribution of the data using some density-based methods. In generative models, they still want to learn the distribution, and AutoEncoders, something like that. So then their assumption is whatever you have is normal, and whatever is not similar to the thing that you have should be anomaly, should be outlier. In unsupervised anomaly detection is like when you know nothing about your training data. So it means you don't know what is normal, what is not in your training data. But the thing that you know is they have some property, as I said. As it means they are not similar to the rest of the data, and they are different. So it means the density of the data that they have should be like a super small, or they should be far from the other part of the data. That's why here we have like a density-based model, which means a data point that is far from the rest of the data is maybe fraud. Or in a clustering-based model, you're making lots of cluster and saying that if a cluster have some super few sample in it, maybe that cluster is fraud. And yes, so if I wanna group them in different way, which for the sake of the workshop, I kind of categorize them in 3 different new way for myself, which was if those methods if they are statistical methods, if they're classical machine learning methods, or if they're deep learning methods. And I was saying that the statistical method is like whenever you are using some statistical model like GMM, that you're saying maybe as simple, it can be as simple as that you're just fitting a Gaussian model on top of your data, and if some sample is far from your mean, you're saying that maybe that sample is fraud. In classical machine learning is when you're using let's say not deep learning models, which can be like 1SVM, k-nearest neighbor, or it can be like an isolation forest. Those algorithms that they're kind of classical, but they are using different techniques to be able to catch all those fraud in your data. And the last one is deep learning based approach, which means whenever you have a bit of complexity in your data, that you can't just handle your data super easily. Like if you're dealing with sequential data or image or some kind of data which is super hard to be handled by some simpler machine learning model. Like for us, whenever we are dealing with healthcare fraud, usually is like a hierarchical. A person might submit a claim. That person has a sequence of claims before that, and each claim has lots of, let's say, medication code, demographic information, the place that is visiting, the length of a stay, the cost, the duration, all those things that are related to that claim. And to be able to catch the fraud, given all those complexity in your data, sometimes you have to actually use some deep learning based model so they can kind of capture maybe hierarchical relationship in your data or some more complex pattern in your data. So here, I just mentioned 3 items here, which one of them was autoregressive neural network. Like if you can learn the distribution of your data, you can use it and say that whatever deviates from it is not from the data. It's like for image, it's like pixel CNN, which is like autoregressive model that try to learn the distribution of the data and the probability of that image sample in your data. Or something like language model. When you're doing language modeling, you're predicting the next word as a prediction. And if you combine them, then you can say what is the probability of a sentence, of a given sentence. And if some of the word or some of the things are super different, then you can say that maybe that sentence is not a normal sentence, and maybe it's outlier. In AutoEncoder, the idea is like learn to reproduce your input. It means given the input, if you can reproduce it, then you should be able to learn what's inside, learn the pattern from it. That's why you can kind of regenerate it. And if you can regenerate a new sample, maybe that sample is not from the training data. And in Gans, is like the idea in Gans is like they want to learn the distribution of the data so they can actually generate a new sample. And the discriminator is there to be able to tell the difference between fake and real. So if you have that discriminator, you can kind of use it to say what is fake or anomaly from the actual data. So there are different ways that you can look at it. but there are lots of deep learning methods that we can talk about, and that's why I kind of list a few of them here.
We have another question related to the slide you just presented. If you take another question.
Sure.
Sakura was wondering, is discriminant analysis like LDA or QDA belong to this discipline?
Which discipline?
The discipline of anomaly detection. Like, how does LDA or QDA fall into this? Are they relevant, or I think that's what he means.
If you're saying discriminator, you mean by LDA, I guess you mean linear discriminator analysis, not for topic detection. So the thing is, like, if you are talking about discriminator models, the thing that they're trying to learn is, as you know, is like p of y given x. Is like they want to learn what's different between your class if it's supervised. If they want to discriminate between two maybe class, they are not actually learning the distribution of the data. That's why I was mostly trying to say that the thing that I was looking for is mostly the generative model, that they can learn the distribution of the data. So if you have any kind of data that they can learn the distribution of the data, you can use them all. So it can be, so it shouldn't be just so the way of thinking is like, even I was trying to say that in a deep learning based model, which was maybe like a self-supervised learning model or generative model, here is like, you can kind of apply any kind of machine learning model as far as you can say that if you can define a good task for it, and then you're saying that if a new data is not following all the pattern that I've seen before, maybe it's fraud. So it can be basically be any task, or it can be maybe self-supervised learning tasks, like given a claim, you want to predict maybe the cost of the same claim because the cost is part of the claim, and if you can predict the cost given the rest of the claim, so it's like a self-supervised learning. So then if the prediction is off for a new claim, then maybe something is actually off about the claim itself, and maybe it's a fraud, or maybe it's outlier. So and that self-supervised shouldn't be deep learning. It can be actually any normal machine learning as well. So as far as we can define some good task or something that actually can tell the difference between normal and not normal, then it should be good to go. I hope I have answered that question.
Okay, thanks.
So for the deep learning base, these are the things that we actually, as I said, we will talk about them in more depth in the upcoming workshop. That's why I was trying to do some brief overview here, so that we can kind of learn from them, see what is the category and what are some approach that we can handle. And for sure in the workshop, we'll try to talk about them in more depth, and we will try to implement them as well. So here, for the deep learning based approach, some of them, as I say, is like a deep leaf network that you want to learn the distribution based on RBF, or even like layer-wise autoencoder, or a generative model by itself. So for generative models, it can be, instead of autoencoder, it can be just like a variational autoencoder or adversarial autoencoder, or all those GAN generative adversarial networks that they are trying to learn the distribution of the data so they can generate a sample from it. And to be able to generate a sample from your data, you kind of need to learn the distribution of your data as well. And it shouldn't be as, so generative model, here I was just talking about deep learning, so it can be even not deep learning model as well, like even a hidden Markov model that it's trying to learn the distribution of sequential data is a good generative model that you can use it, and then you can say that maybe a sample is off. And for sequential model, it can be something like ARN as well. So like language model that I mentioned, or it can be like a AutoEncoder, RNN autoencoder as well. So as far as you can learn the distribution of your data in a way that you can predict maybe the next word, or you can predict the whole sentence again, or you can do some semi-supervised one on top of it, like something Bear's doing to be able to make a good representation, sometimes trying to just fill the blank. And if you can do that, then it means you have a good understanding about the context. And if your understanding is super off, then you're saying that maybe something off about this sample, this sentence, and maybe this is outlier. So all these models trying all I was saying here was using different models, not just one model. It means AutoEncoder, as I said, try to reproduce the data again. Self-supervised just trying to reproduce maybe a part of it. Generative one trying to learn the distribution, and all these models try to learn something from the data. So from that moment, they can say if you are different from whatever I have seen before, and that can be a clue that can tell you that if you have an anomaly in your data, or if that sample is a noise. And for sure, to be able to have a perfect anomaly detection, which we have in notions, is like if you have an ensemble of all of them, because each of them can capture different type of anomalies sometime, and having them all as a different method and having an ensemble on top of them, then you should be able to have a better understanding of your data and be able to capture anomaly in a better way. So here I just was trying to briefly talk about one of the method, which was like isolation for us, which basically means one of the classical model, which is build a decision tree to see how many random split on random feature it take to isolate each data point. So if you can easily isolate a point, maybe that point is anomaly. And if lots of points are tightly together, isolating that node would be hard for a tree or for a forest of tree to be able to do that. That's why you can say maybe that's not a fraud. The idea is as simple as that. So you can view them as a subspace method that use, as I said, an ensemble of isolation tree. Each tree is like an unbalanced tree constructed from a small sub-sample. And the only thing that they're trying to do is like making a new sub-sample. And if like in the upper picture, they could by just drawing few lines, they could kind of isolate the x0, but to isolate the xi, it should be super harder for us for a decision tree to do that. That's why the score here is the average length from your sample to the root. It will be the score of your anomaly, something like that. So there are different methods. One of them, as I say, is like a isolation for us. One of them can be like a KNN. So the idea in KNN is like they're saying that if a point doesn't have that much neighborhood within a predefined distance, then maybe that point is anomaly. So and if you want to look at maybe more of a kind of like a deep learning models, one of the basic one is AutoEncoder, which you're trying to reproduce your whole data again, which means you don't have to have any kind of information about it that much, because that's why which is one of maybe the drawback of self-supervised one. Here, the only thing that you want to do is you're saying that that's my input, reproduce it again, which one AutoEncoder will just pass it through multiple layers, and it means to be able to compress it to a few nodes in the middle layer, you should be able to capture and extract those patterns from the data so that you can use those patterns to be able to reproduce it. And if you can't do that, then you can say that's off. So there are different models in AutoEncoder part. It can be vanilla AutoEncoder, it can be variational AutoEncoder that you are kind of imposing prior to the latent layer, which is like a middle layer, or it can be adversarial autoencoder, which kind of using the Gans technique to kind of restrict the middle layer to be like your prior distribution, which can be like a Gaussian or anything. And for the encoder and decoder, you can just use dense, or if you're maybe looking at the image, it can be CNN. If it's time series, it can be RNN. So based on your need, you can have different encoder or decoder, and you can try different model to see which one of them will give you a better result. And we'll discuss them in more detail in the workshop as well. And just to give you maybe a more brief overview of how it can be look like is like for if you have an image like a MRI image, and you want to say if something is off about that image, if that person has a tumor or not, you can just try to reconstruct it. Using here is just the first image is just like a regular autoencoder. The second one is a variational autoencoder that you want to reconstruct it, and then you're comparing the reconstructed one and the actual data, and you're saying that if the difference is super high, then maybe there's something about this image that I haven't seen before in the training data. That's why the model can't reconstruct it again, and that's why you can flag it as anomaly. The other method, which was super interesting, and you can see lots of new papers about it, was Gans. So basically, Gans tried to learn the distribution of the data. One of the Gans job is to learn the probability distribution of training data. And as you know, GANs are like a framework for estimation of generative models via an adversarial process. And here the discriminator D, using a discriminator D and generative G, so the G trying to make a new sample, like a fake sample, and the discriminator should be able to tell the difference. And using like a adversarial process, they will get better and better. So the generative try to make a kind of like a real data, and still the discriminator should be able to tell the difference. And that's the idea, a brief idea about what's GAN. And it means if you have enough data, and the GAN in theory and on paper should be able to learn all the distribution of your data and should be able to generate a sample from it. And if you want to use it as an anomaly detection, you can kind of convert this GAN to be like a conditional GAN. It means given the input, you want to regenerate that input again. So the generator can be just, here is like I just mentioned like a bit more complex version of it, but it can be just a regular autoencoder. Given an input, you want to reproduce that input as as output for your generator part of the GAN, and instead of just computing the difference from the output and input, you can use a discriminator to be able to tell the difference. It's kind of one of the reasons that people switched to GAN was whenever they were trying to regenerate an image or generate a sample or make a sample from your distribution using variational autoencoder, you're saying that it's blurry or is not clear. And GAN was able to solve the problem because instead of using any Euclidean distance or any kind of metrics that you want to tell the difference between input and output, you are using a discriminator that its job is to learn and to be able to tell the difference. And here they're kind of doing the same thing. They're kind of using, here is like a variational autoencoder GAN model, which using variational autoencoder, they're trying to regenerate the sample, and the discriminator should be able to tell the difference between the reconstructed one and the input one. And so at the very end, if something is off about the sample, this model should be able to tell the difference. It's like the discriminator from that moment should be able to learn what is the actual data and what is not. And just as a sample of a bit more complicated version of it, which was a paper with cool name, which was Anomaly, it was using, as I said, like an autoencoder for the generative part, and for the discriminator part, it was maybe you can just say that it was like a encoder again as well. So it was using 3 different laws to be able to say that if something is real or not. It was trying to tell the difference between the generated one and the input one, and then the discriminator should be able to tell the difference, and then it just add another encoder at the end of the generator. So if they're comparing the latent space representation to see if they are similar or not. So it means they're kind of trying to compare the input and maybe the generated one in different way, in the actual space, in the latent space, and they have a discriminator to be able to tell the difference, to kind of make sure that if they are saying, so the GAN can learn and be able to tell the difference between the normal one and not normal one in your data. And if you are interested to learn more, we are going to have a workshop called Modern Recipe for Anomaly and Novelty Detection. I guess it's going to start next week. And we will talk about all these methods in depth, and we'll try to implement them and to see which one is better for which application, and given different type of data, what should you do to be able to capture the anomaly and to be able to find those novelty in your data. Thank you.
Oh, okay, great. So we have a few questions lined up. But before that, on that note, now that you mentioned the workshop, it starts on Thursdays next week. You can either join online or in person for those who are new to our offerings in general. And we have a discount code that you can apply if you apply within the next 48 hours, I believe. The discount code is launch. And before you check out, if you apply the discount code, you can get an instant $30% discount. And if you have been a member with us for a while, and you probably are aware that you have a personalized discount code, and you can use that to get, typically you get a bigger discount. So you can follow the link on the screen to learn more about the workshop. So we have a few questions about the presentation and topic and the workshop. So it seems that there is a general, I think we have a few questions about this. I understand you mentioned this in a couple of slides, but could you do a sort of recap on how generative model helps detect anomaly? I think you mentioned in a few slides, but if you could do a recap and just do a summary of that, that'd be great. And that seems to be a common question, like in the thread right now.
So here, because I want to say something brief, it's going to be like generative model is they're trying to learn the joint distribution of the input and the target together. So it means basically the thing that they want to learn is, given y, what's the probability of x? That means the generative model try to learn the distribution of the data. So given that you have trained a model, a generative model, and you kind of have a model that can tell the likelihood of a sample in your data, then once you have a new sample, then it will give you a new likelihood. And if the likelihood is super off, you can say that this one might be not part of my training data, so it might be anomaly or outlier.
All right. So Anil asked a more concrete question, also related to this. So you showed a brain scan image in one of your slides before. Yes. So let's say one such scan has a tumor present in it. In that case, the reconstructed output won't have the tumor in it and will be considered as an anomaly. Is that how it works?
Yes, kinda. Yes. So it means like the AutoEncoder is just a bunch of layers that will do its best to be able to minimize the loss, which the definition of a loss is the difference between the input and output. So it means it will try to compress the data and then to be able to decompress it. So the AutoEncoder, you can see it as a nonlinear version of a PCA, which if you do apply a PCA, you will learn the distribution of your data. And from that moment, if you have a new sample which is not following the same distribution that you have seen before, you can say that then you won't be able to reconstruct it again. So it means if something is off about the input data, it can be image or it can be anything. If something is off because the network hasn't seen it before, the constructed one would be a bit different from the input, and that's why the loss would be higher. And you can use that loss to say that maybe there is something off about the input, and maybe the input is outlier.
Okay, that makes sense. if you have more questions, we're a little bit running out of time, but if you have questions, further questions on this, feel free to discuss on our Slack channel. If you don't know about Slack channel, just go to ai.science/register, register for an account. Registering is free. So we have a question about the workshop. So basically, Sakar, I hope I said his name correctly. Sakar is wondering if there's any pre-reading pointers before attending the workshop. So what are some of the prerequisites like that people should read before attending the workshop?
I believe because the structure for the structure of the workshop is a bit different now. It means I guess I'm recording some videos before each session.
Correct.
Am I right? Okay. So then it means I will share a bunch of new papers and some readings that you can actually read beforehand. I will do that, and before each session, I will record a video. It can be maybe like an hour video, so you will see it before attending the workshop. And I guess the first maybe 20 minutes and half an hour of the workshop, we will answer any question about those things that we discussed in the video, and then we'll try to implement those ideas. It's like I will have one session maybe talking about all those autoencoder, rational autoencoder, and the GAN that you can actually use to be able to detect different type of anomaly or fraud in your data. And then in that actual workshop, we'll try to implement them and see what's the difference between them and how can you actually use them.
Okay, yeah, that's right. So like Rohollah just mentioned, so we give you plenty of time, usually a few days ahead of time. We release the lecture video so that you can watch at your own pace. And actually during the workshop, we actually do expect you to at least have watched the lectures. It's usually a 1 hour long, so it's not very long. And during the workshop itself, we will focus mostly on asking questions, going back and forth, and doing more hands-on part. For those who join online, we have a dedicated TA, Willie. I think Willie's here today in the chat room as well. He will also be. We'll have a dedicated TA to have a conference call, so to answer people's questions, so that you can feel as if you're attending a live workshop. So we have another question about AutoEncoder and GAN. Let me try to understand this correct. So the question is, can you use the GAN discriminator outside of an autoencoder?
What do you mean outside of the autoencoder?
To be
okay,
honest,
let me talk about maybe a bit briefly that what I mean by that. So it means, okay, first of all, we can start with the GAN itself. You can say that if the generator part is good enough, so it can actually produce a good fake data. The only job that discriminator has is to be able to tell the difference between the generated one and the actual one. Usually in all those GAN community for image or for all those things, they mostly care about the generator part, which means they want to be able to produce or reproduce a good picture, good quality picture, which kind of exactly like the normal one. But they are a bit off, they are not real. And the only job that the discriminator has is to be able to tell the difference, to say that what is not normal is like, as one of the application that I said, maybe fake news or fake image or fake video, to be able to tell the difference, you need a good discriminator. So yes, the discriminator by itself, if it has been learned using a good amount of learning, and I don't know, if you have good data, if generator part is covering all the data, yes, the discriminator should be able to tell the difference between fake or real, or you can say novelty or not, or normal or something like that. But to make the generator part to cover all the data and to be able to learn the distribution of the data, they are using like a conditional GAN, which is maybe, as you said, as you saw, it was like a autoencoder, because like the image or the input is itself is a condition that the generator should look at it and be able to generate something like that, and then the discriminator should be able to tell the difference. So that's why they're saying that in some scenario like that, the generator will cover all the data, and it still should be able to make super real data, but it won't be real. And And if you have something, a new data which is a bit off, the discriminator should be able to catch it.
Okay, so
I was trying to, yeah.
He actually clarified his question, so he put it in other words. Can you use the discriminator to predict whether the input is fake without having to run it through the GAN?
Which means, okay, the discriminator itself is a classification method. It means if you completely remove the generator part, the generative is given input in that scenario. It will try to generate something which can be autoencoder or anything. If you just look at the GAN, it means given any maybe noise or something, you want to generate it. It's like a decoder part of a autoencoder. And the discriminator part is like a maybe encoder part of autoencoder, which given an image, given an input, it will try to map it to maybe a two. Let's say for classification, you want to map it to two-dimensional space, latent space, which we are kind of enforcing it to say that if that value is more than 0 or more than 1, so based on your criteria, it is off or on. So if you don't have any generator, if you don't have a GAN, and if you just have discriminator, you're just looking at a classification problem, which was one of the method that we discussed, which was like a supervised way of detecting it. But for that, you need a label data.
Okay. Yes, that totally makes sense. Okay, just a reminder. Hopefully, Aaron, hopefully that answered your question. Just a reminder. Don't forget to use our discount code if you want to register the workshop. Everybody gets a discount code. So if you have any further questions, feel free to join us. Register at AISC.ai.science. Register online, join our community, and discuss there whether you attend our workshop or not. And with that, we're almost running out of time. And thank you. I'd like to thank Rohollah to take the time to present this wonderful presentation to us. And thanks everybody. We have a lot of people in the chat room today, a lot of active discussion. And thanks everybody for attending. And our next event, I think it will be on Monday. It will also be live streamed. So please make sure to check our website for regular events. We do our events very frequently, and we do workshops about every month, one workshop per month. Thank you, everybody, and I'll see you next time. Thanks, Rohollah.
Thank you.